Hey everybody, I'm back here. Let's go ahead and now use what we learned about power functions to determine the end behavior of this graph. Now I have three terms in this polynomial, but I'm really only interested in the leading coefficient, or the leading term. And again, that doesn't mean the first term. It means the one with the highest degree, the highest number exponent. And so in this case, this is what I'm looking at. I'm not even, when it comes to end behavior, I'm not even considering what else is happening. I'm just looking at this term. I know that the degree is 3, which makes it odd. So this is an odd degree polynomial. And like we talked about with end behavior, an odd degree has a basic shape that starts high, ends low, or starts low and ends high. That's going to be determined by the leading coefficient, which in this case, the leading coefficient is -2, which is less than 0. And so that's going to be this second case here, where I start high and I end low. And the way that we write this, determine the end behavior, the way that we write it is we say as x goes to -infinity, meaning starting all the way on the left of the graph, my graph should be starting high, which is +infinity, and as I go as far right on the graph as I can, my graph should be going down or headed towards -infinity. And that's the picture we have here. We're starting high, we're ending low. But again, we're starting at -infinity and going this way when we read the graph. So this is the start and this is the end. So as x is headed this way, my graph is going up. And as x is headed this way, my graph is going down. That's what we just said in this sentence here. And this is how you would answer the question, determine the end behavior of a graph. Okay? So let's talk about the zeros of a polynomial. A polynomial function of degree n will have at most n real zeros. And that's really helpful. This is actually, well, the fundamental theorem of algebra says that the number of zeros, whether they're real or imaginary, is equal to n. But what we know is that we're going to have at most n real zeros. We're going to have at most the number of x-intercepts on the graph will be the number of the exponent that is in the leading term of the polynomial, okay? And I want you to know that a 0 or an x-intercept or the solution of the equation f of x equals 0 or a root, these are all different words that mean the same thing. We're talking about on the graph of the polynomial, where am I crossing the x-axis? These are important points. This is what we're finding, real zeros, okay? I want to actually be able to see it, touch this, or go through the x-axis. It could also do this. That's also a real 0 right there, okay? So the way that I find zeros is the same way I find zeros with anything else. Factoring is the easiest or the quickest way to find the zeros of a polynomial, and that includes quadratics, that includes lines sometimes. We don't typically factor because there's just the one variable term, but you could also factor lines, linear equations to find the zeros if you wanted to. All right, so what this is really saying, this first one is already factored. F of x is factored. So really it's saying find when this graph equals 0. That's why they're called zeros. It's when the coordinate, I'm looking for some x value where the y value equals 0 on the graph. And so we're just going to use the zero product property here. And we know that if this whole expression equals 0, that means that either x minus 1 equals 0, or x plus 2 equals 0, or x minus 3 equals 0, which means that x equals 1, x equals -2, and x equals 3, which are the coordinates. Now, I know a lot of people have been typing the coordinates into Pearson MyLab. Usually when they're talking about x-intercepts, they just want 1, -2, and 3. They don't want the coordinate. I think it's proper to say 1, 0, -2, 0. And I've been going back and giving people credit for writing these. But if you want it to get marked right the first time, don't write the coordinate 1, 0. Write the number 1. Okay? Now, if you're putting a vertex in there, I'm going to look for an x and a y coordinate. And they'll say ordered pair, or they'll say type in a number or decimal. Okay? So you'll know the difference. So these are the real zeros right here. 1, -2, and 3. And you can also write it x equals the set containing -2, 1, and 3. Okay? Now g of x is also factored. Okay? So if I want to find the zeros, I'm just going to set this equal to 0. And in this case, x equals 3 is a 0. That happens twice because this is really, g of x is really x minus 3, x minus 3, x plus 1. So this one actually happens twice, and we're going to talk about multiplicity in just a minute and what that means for the graph. But this is twice that this is happening. We only have to write it once, but it does happen twice. And x equals 1 is also a 0. Okay? Now h of x is not factored. And we have 4 terms here. And anytime I see a polynomial with 4 terms, my first attempt at trying to factor it is going to be to use the technique called grouping. So I'm going to factor something out of the first 2 terms that they have in common. The greatest common factor here is x squared, which leaves me with x plus 2. And then the greatest common factor in the next 2 terms, you could say 1, but I want what's left over to be x plus 2 again. So I'm going to factor out a -1, and that leaves me with x plus 2. Now the reason I want to factor it in this way is now I have 2 terms, 1, 2. Okay? Term 1, term 2. And in both terms, there is a common factor, x plus 2. So I can factor that out, and I'm left with x squared minus 1. Okay? And again, if I multiply this through, x squared times x plus 2 gives me this back. And if I multiply x plus 2 by -1, I get this back. Okay, so it works. But I'm not done yet, because right here, this is like the gift that keeps on giving. Right here I have the difference of 2 squares. So I have my x plus 2, but then I also have x minus 1, x plus 1, and these are all equal to 0. So my zeros are -2, 1, and -1. Those are my zeros right there. And again, on the graph, if I was talking about the points on a graph, I would write these as ordered pairs. If I was talking about x-intercepts, I would want them as ordered pairs, but Pearson MyLab just wants you to type in -2, 1, and -1 separated by commas. So as long as you have this in there, this would be the correct answer on Pearson MyLab if they were asking for x-intercepts. Okay? All right. So, in the last example, I talked about this problem here where 3 occurred more than once, and that's the multiplicity. Okay? Now, you can tell the multiplicity if you're in factored form and you have an exponent. The multiplicity is that exponent. So zero is a root or is a root of this polynomial. It's an x-intercept. The point 0, 0 is an x-intercept. The multiplicity of this 0 is 2. 2 is the multiplicity that describes that 0. The multiplicity of this 0, 1, 0, is 1. And the multiplicity of this 0 right here, -2, 0, is also 2. Now, if the multiplicity of a 0 is even, what that means about the graph is that you're going to bounce off the x-axis and not go through it. Okay, so you're going to touch the x-axis, but you're not going to go through the x-axis. So you can see that at negative 2, 0, my graph bounces off the x-axis. Okay, and then at 0, 0, because the multiplicity is even, again, the graph bounces off the x-axis. And then at 1, 0, because the multiplicity is odd, the graph goes through the x-axis. And if you think about what's happening at each of these points, this is if I ignore everything else here, okay, this is x squared. Okay, it's an x squared term, right? And what does the graph look like? Really close to negative 2, this looks like a quadratic. Okay, and then at, sorry, it's this one that was doing that. So this is a quadratic, right? This is a quadratic. This is a line, okay? And right, if we like really zoom in on the graph, it's just going to look like a quadratic at both of those spots and a line there. So if you had something with a multiplicity of 3, it would look cubic. So it would look like this at those zeros that have a multiplicity of 3. Your graph would do something like this, which is what a cubic looks like. Or it might also do this, just like these points could have also come up from underneath. So that's what multiplicity is. So all you have to do is you have to have a polynomial in factored form and then look at the exponent of the factor that produced the 0. So this factor produced this 0, and the exponent was 2, so the multiplicity is 2. This factor produced this 0, and the exponent was 1, so the multiplicity is 1. This factor produced this 0, which has an exponent of 2, so the multiplicity is 2. This is a tough concept for a lot of people. So again, if you need to pause and rewind and rewatch, please do so. And again, please do the practice problems that are in the study plan for these kinds of things.